Very good morning to all of you. Today I want to start lateral earth pressure. This is the most important topics in geotechnical engineering, and it is the very fantastic topics. I hope this topic is last unit in these subjects. Okay, now I want to cover this second part of module 3, that is lateral earth pressures of module 3 session 5. Course outcome of this lateral earth pressure is given by to compute lateral pressure distribution behind earth retaining structures. Okay, course outcome is to compute lateral pressure distributions behind earth retaining structures. Title of subject is Applied Geotechnical Engineering, and the subject code is 18 CV 62 in 6 semesters of Civil Engineering Department. Okay. Contents. Today's session 5, I want to cover in details about lateral earth pressures and earth pressure at rest or at rest earth pressures. So these two contents, that is introduction about lateral earth pressure and at rest earth pressures, or it is also called earth pressure at rest. These two sections are required to complete in session 5 of today's class. Let us see introductions about lateral earth pressure. See, this is the diagram. This is the embankment. Okay, this is highway embankment. See, this is the backfill. This is the original roadway. This is road width, that is original roadway, and this is extensions, that is footpaths. Extension, and this is retaining walls. We are constructing retaining walls to protect the backfills. Of one side it's shown here, this side also shown saves. Okay, and see, this is figure B with respect to retaining walls. This is retaining walls, and this side is backfills. This is ground surface. On the top of the surface, that is earth structure, houses are constructed. Okay, now see, this is the good examples of lateral earth pressure explanations. Lateral means horizontal pressure is occurred by soils. So due to load is acting on the soil, so that pressure is developed due to self weight of the soils as well as due to live loads, earthquake loads, wind loads, etc. So now our structure is required to stable as per the design criteria. To minimize the crack, to protect the sloped structure, we are constructing a retaining walls. That retaining wall is related to the lateral earth pressures. Pressure is most important here. To minimize or to avoid or to protect or to retain the pressure, left side and right side there are a retain wall is constructed to prevent the lateral earth pressure in terms of active earth pressure or passive earth pressure or pressure at rest. So that's why nowadays we are seeing in so many structures at highways embankments or roadway embankments or canal embankments or buildings are constructed in hilly area or sloped structures, retaining walls are constructed to prevent the lateral earth pressures while constructed by backfills materials. So that backfill is are used by different type of earth materials. Okay, so based on these two diagrams I will explain here. Retaining walls are structural members used to support vertical or nearly vertical soil backfills. This is usually needed when there is a change of grade. A retaining wall, for example, can be used to retain the backfill required to widen a roadway as shown in figure 7.18, or to retain a backfill that is used to support a structure as shown in figure 7.1b, that is retain structures. So to retain this structure, retaining wall is constructed. To retain the road embankment or to retain the road embankment of backfill, constructing the retaining walls. There are several types of retaining walls, including the traditional gravity, semi-gravity, cantilever and counterfort retaining walls that are made of plain and reinforced concretes, shown in figure 2. Okay, so that is, these are the different type of retaining walls. See, this is gravity wall of plain concrete type retaining walls. Okay, this side is backfills, and this is reinforced concrete cantilever backfill walls. So before that I will explain here. So this is semi-gravity wall. It is reinforcements. We are provided reinforcement here. So this is semi-gravity walls. This is backfills. See this figure. This is the cantilever wall. So this is cantilever type retaining walls. This is called reinforcements. This is backfills. And this is counterfort retaining walls. This is counterfort retaining walls. So this is called counterfort wall, and this is called counterfort. This is counterfort. This is counterfort wall. So these type of retaining walls are used in structures to protect the backfill. So this side is backfill. To constructing gravity wall, we are protecting backfill. We are constructing reinforcements to protect this backfill. We are constructing cantilever wall to protect these backfills. We are able to construct counterfort type retaining wall to protect the backfills. So these types of retaining walls are designed by required dimensions based on the loads and based on the earth pressures. Retaining walls can also be constructed from other materials such as gabions, reinforced earth, steel and timber. Nevertheless, all retaining walls have to be designed to resist the external forces applied, and that includes lateral earth pressure such as load, hydrostatic pressure and earthquake loads. I have already explained. Okay, all these retaining walls have to be designed to resist the external forces applied, and that includes lateral earth pressure, surcharge load, hydrostatic pressure, and earthquake loads. There are three possible types of lateral earth pressure that can be exerted on a retaining walls. There are three possible types of lateral earth pressure that can be exerted on a retaining walls. That is, one is at rest pressure, that is pressure at rest, active pressure, and passive pressure. These three pressures are occurs practically. At rest earth pressure occurs when the retaining wall is not allowed to move away or towards the retained soils. It's very clear definition. Pressure at rest occurs when the retaining wall is not allowed to move away or towards the retained soils, or that is backfill soils, is called as earth pressure at rest or at rest earth pressure. And active earth pressure occurs, it's defined when the retaining wall is permitted to move away from the retained soil. See, this is very fantastic sentence, this is very important sentence. Active earth pressure occurs when the retaining wall is permitted to move away from the retained soil or backfills, is defined as a active earth pressure. The active earth pressure produces a destabilizing, the active earth pressure produces a destabilizing earth force behind retaining walls. Okay, the active earth pressure produces a destabilizing earth force behind retaining walls. And passive earth pressure is nothing but a, on the other hand, develops, that is passive earth pressure develops when the retaining wall is forced to move towards the retained soils. Develops when the retaining wall is forced to move towards the retained soils, means towards the backfill, that is called passive earth pressures. Granular soils are usually used as backfill materials. Granular soils are usually used as backfill materials behind retaining walls because of their high permeability. Because of their high permeability, that is freely draining materials. Using granular fills along with the weep holes, that is small openings in the retaining walls, prevent the accumulation of hydrostatic pressure during a rainfall. Okay, so nowadays you can see towards where there is a highway work is going on, so this concept is used, weep holes they are providing. Okay, other types of drains are available. Other types of drains are available, including perforated pipes that are commonly installed at the bottom of the granular fill directly behind the heel of the retaining wall to facilitate drainage. So this type of concept is used in highway constructions. In highway district also, same this technique is used. Soils such as sand, gravel, silty sand, and sand with gravel are good backfill materials. Which type of materials are used for backfill material? Sand, gravel, silty sand, and sand with gravel are good backfill materials. These are the available materials are used. You decide by using these type of material and you used as a backfill materials. Cohesive soils are not desirable as backfill materials because of their low permeability. So that is the main reasons. Cohesive soils are not desirable as backfill materials because of their low permeability. So in permeability chapters, we have already learned how to calculate the variation of the effective vertical stress in a soil strata. So that is to calculate total stress, effective stress, neutral stress. We have already understood in GT1s, that is permeability chapters. Now we can calculate the effective lateral earth pressure by multiplying the effective vertical stress by an appropriate lateral earth pressure coefficients. By appropriating lateral earth pressure coefficient at rest, active or passive. That is coefficient of value we are calculating to calculate earth pressure at the base. The at rest lateral earth pressure coefficient K0. At rest lateral earth pressure coefficient is K0. Can be estimated using the empirical equation K0 equal to 1 minus sine phi dash 1 minus sine phi dash. Okay, as per the Jackie 1944s, where phi dash is the internal friction angle of the backfill soils, where phi dash is the internal friction angle of the backfill soils. The active lateral earth pressure coefficient Ka, the active lateral earth pressure coefficient Ka can be calculated using the equation Ka equal to 1 minus sin phi by 1 plus sin phi. You remember these equations. To calculate coefficient of active earth pressure Ka, the equation is 1 minus sin phi by 1 plus sin phi dash. So here phi is nothing but the angle of internal friction of backfills. Whereas the passive lateral earth pressure coefficient Kp can be calculated using the equation Kp equal to 1 plus sin phi by 1 minus sin phi. You remember these equations. Okay. Coefficient of passive earth pressure coefficient Kp can be calculated using the equation Kp equal to 1 plus sin phi by 1 minus sin phi. It can be seen from these equations that both the at rest earth pressure coefficient and the active earth pressure coefficient are smaller than 1. Okay, it can be seen from these equations that both the at rest earth pressure coefficient and the active earth pressure coefficient are smaller than 1, and the passive earth pressure coefficient is greater than 1. Passive earth pressure coefficient is greater than 1. This means that in soils the lateral stress is not equal to the vertical stress for any possible condition at rest, active and passive. This is unlike the stresses inside a fluid which are equal in all directions, as you have learned in fluid mechanics. Okay, so we have already learned in fluid mechanics how stresses are cuts in fluids. If water is present in the backfill behind a retaining wall, if water is present in the backfill behind a retaining wall, the water pressure should be added to the effective lateral earth pressure exerted on the wall. Figure 7.3 shows, see, this is figure 7.3. So this is retaining wall and this is top surface of retaining wall, and this is water tables. So this is water tables and this is backfills. So this is backfills, and see from this elemental area horizontal stress and vertical stress due to water. See, this diagram is explained, that is backfill soil particles, how water pressure is occurs, how water pressure is developed with respect to granular materials if the water table is present in the backfills. See, these are the soil granular soil particles. Okay, see these gaps are water is filled, that is U is the pore water pressures. See, these are the pore water pressures where there is a white gaps. These are the pore water pressure, and these are the gravel particles. In this directions, horizontal pressure is x, that is sigma h dash. It is sigma h dash. See, this is sigma h dash. See, this sides water pressure is flow takes place in horizontal direction, so that is horizontal. Effective lateral earth pressure is x in these soil particles. So that's why this diagram is explained for lateral pressure on a retaining walls. Okay. From figure 3 above shows details of a soil element in a contact with a retaining walls. Two types of pressure are exerted on the wall by this fully saturated soil element located at some distance below the water tables. See, this is the soil elements. So these are two soil elements. One is sigma dash h, sigma dash v. Vertical pressure acting in y direction, vertical pressure, horizontal pressure acting in x directions. Okay. The first pressure is the one exerted by the grains and denoted as sigma dash h in the figures. This is sigma dash h, first pressure. This is by definition the intergranular stress, known also as the effective stress. Intergranular stress, known also as the effective stress. The other type of pressure is the pore water pressure, caused by the water filling the interconnected voids is nothing but a pores, and denoted by U in the same figure. See, this is U. So these are the water filled. This is U. Okay. The retaining wall fills both sigma h dash and U. Therefore, these two pressures should be considered when calculating the lateral earth pressure exerted on a retaining walls. So that's why effective pressure as well as water pressure is also considered to calculate lateral earth pressures on a retaining wall. Now see at rest earth pressures or pressure, lateral earth pressure at rest. It is also called as a neutral pressures. Okay. See these diagrams. So this diagram, see, this is the retaining walls. This is bottom width. This is top width or top surface of the retaining walls. And this side a backfill is there, and this is friction angle is 0, and here soil element of pressure, effective stress along x directions as well as vertical stress along y direction also we are considering here. And here sigma h dash equal to k naught times sigma v, means sigma h by sigma v, we know that k naughts, that is earth pressure at rest. Okay, so this horizontal pressure in x direction is equal to k naught times sigma dash v. So now see, this is the most circles, stress strain diagrams. This is y axis is shear stress, x axis is normal stress. Okay, most circles, most failure envelope we have already seen in shear strain chapters. Okay, and this is from here to here sigma h dash, and here to here sigma v dash. Okay, and this from here to here deviator stress or earth pressure at rest, and this circle we are defining as a Moore circle at rest condition. Sorry, and this we are considering as a Morse Coulomb failure criteria. This is Moore Coulomb failure criteria. And this sides we are considering as a phi dash, and this distance we are considering as a c dash. Okay. So from that figure 4, consider a soil element in a contact with a retaining wall that is restricted from lateral movement, that is as shown in figure 4a. See, this is considering soil element. Sigma V dash, sigma H dash equal to K naught times sigma V dash. The at rest lateral earth pressure is calculated by multiplying the effective vertical stress by the coefficient of lateral earth pressure at rest, that is K naught. This coefficient can be determined experimentally for a given soil by restraining the soil from lateral movement and subjecting it to an effective vertical stress sigma dash V. This can be done using a rigid container filled with soils. This can be done using a rigid container filled with soil. The resulting effective horizontal stress, that is sigma dash H, exerted on the sides of the rigid container can be measured by means of a load or pressure cells. Therefore, the coefficient of lateral earth pressure at rest can be calculated as K naught equal to sigma dash H by sigma dash V. Coefficient of lateral earth pressure at rest is calculated by the equation K naught equal to sigma dash H by sigma dash V. This is equation 1. The stress state in the soil element is represented by a Morse circle as shown in figure B. Note that the major principal stress is the effective vertical stress, whereas the minor principal stress is the effective lateral stress, because K naught is less than 1. In the absence of experimental results, one can use the empirical equations by Jackie to estimate K naught. It is K naught equal to 1 minus sin phi dash. K naught equal to 1 minus sin phi, where phi dash is the internal friction angle of the soils. Let us consider the retaining wall supporting a dry fill of a height h as shown in figure 7.5a. See, 7.5a means this figure. Okay, this figure. So this is vertical wall of retaining wall of height h and water table at the base, and these are the soil properties, that is gamma, phi dash, c dash. So then how stress distribution diagram is plotted? See here. So this is, draw the retaining walls and draw the bottom horizontal lines, and due to water table the earth pressure distribution diagram is plotted like a triangle. Pressure at the top is 0, pressure at the bottom is sigma dash h equal to K naught times h into gamma. Means pressure means you multiply density of soil into height of that particular layer, that is the pressure. Then you multiply pressure coefficients. So we are getting lateral earth pressures, and that pressure is acting at the CG of the rectangle about the base is h by 3. Center of gravity and moment of inertia, you know already from elements of civil engineering. Okay, so pressure at the base is calculated height of the soil into density of the soil into multiplied pressure coefficient, and that pressure is acting at the CG of the triangle about the base, so that is h by 3. If the water table, second case, if the water table is on the top of the retaining walls, okay, and soil properties are, this is gamma saturated and phi dash is angle of internal friction and soil cohesion is C. So then how to plot the pressure distribution diagram? See here. Okay, this is vertical wall, bottom surface. So this with backfill triangular earth pressure distribution diagram. So this sigma h is K naught times h into density, that is gamma saturated minus gamma d, because water table is at the surface. So then submerged density we are multiplying. So that is submerged density means gamma saturated minus gamma d. So this is density into height into coefficient. We are getting this pressure, and this acting at the base of the CG, that is h by 3, 1/3 of its heights. So this pressure is acting at this side. And due to water pressure, so this pressure distribution diagram is with respect to backfill material, and this pressure distribution diagram with respect to water. So water pressure we are calculating here, U equal to height into unit weight of waters, that is H into gamma W. And where it's at the center of the CG of the triangle about the base is, we know, 1/3 of its height, that is H by 3. So this is P2. P1 is due to backfill, P2 is due to water pressures. If third condition, retaining wall is this, okay, and this is H2, this is H1. Here water table is at a certain distance, that is below the H1, water table at a depth of H1. So then above the water table is dry conditions, below the water table is saturated condition. So then below the water table is density of material is saturated, and above the water table density is dry density gamma. So then how to plot the pressure distribution diagram? See here, see this is, so this is the as usual retaining wall, draw the horizontal lines, and here three pressure distribution diagram is occurs, okay. So one is this pressure distribution diagrams, okay, these diagrams you calculate due to backfill, there are 4 pressure, okay. This pressure distribution, that horizontal lateral earth pressure sigma dash H equal to K naught times H1 into gamma, means this pressure distribution diagram, this pressure is K naught times height into density, that is H1 into gamma, multiply K naught. So these portions, and same is acting here. Next these portions, so from here this is the pressure distribution calculated, that is plus K naught into H2 into this submerged density, that is gamma saturated minus gamma W. So this pressure is acting here from here to here, and this act at the center of the CG, that is H2 by 3, that is P3, and this is P1 acting at a CG of this triangle, that is H1 by 3, and this is rectangle, this acting at the center CG of the rectangle, means half of H2, that is P1, this is P2, this is P3, okay. And this pressure distribution diagram due to water pressure, so this is U equal to H into unit weight of water. H means here H2, this side H2 into density of water, that is gamma W. This act at the center of the CG, means about the base of the triangle, that is H by 3, means here H2 by 3. So this is P4. So like we are calculating pressure distribution diagram as well as lateral earth pressure based on these 3 conditions, how pressure distribution is calculated and plotted the diagrams, okay, with the different conditions, okay. So now here based on those diagrams, okay, from equation 1 we can write sigma dash H equal to K naught times sigma dash V, but sigma dash V equal to gamma into Z. Vertical pressure is calculated in terms of density into depth, that is gamma into Z, where gamma is the unit weight of the backfill soil and Z is the depth measured from the top surface of the backfills. Combining the 2 equations we get sigma dash H equal to K naught times gamma Z. This equation indicates that the effective lateral earth pressure increases linearly with the depth as shown in figure B, that is 7.5b. At the top surface sigma dash H is 0 because Z is 0. At the bottom of the retaining wall sigma dash H is K naught times gamma into S because Z equal to H. The at rest lateral earth pressure distribution is therefore triangular as shown in figure 7.5b. So this is triangular, lateral earth pressure is triangular. The at rest lateral earth pressure distribution is therefore triangular as shown in figure 7.b. The at rest lateral force P naught exerted on the wall is the area of the lateral earth pressure triangle, that is P naught equal to half into base into height. So here area of the triangle we are calculating half into base into height, that is half into k naught gamma h into height is h, means half k naught gamma h square. The point of application of P naught is located at a distance of h by 3, that is CG of the triangle about the base, that is 1/3 of its height, that is h by 3 from the bottom of the retaining wall, because of the triangular pressure distribution. When water is present within the backfill, as may happens during a rainfall, with the drains clogged, the effect of pore water pressure needs to be accounted. Based on these water tables condition, figure C shows a retaining wall supporting a backfill with a water table that is coincident with the top surface of the fill. In this case, the lateral pressure exerted on the wall consists of two parts: the effective lateral earth pressure and the pore water pressure. This is illustrated in figure 7.5d, in which the effective lateral earth pressure and the pore water pressure are plotted separately. The effective lateral earth pressure is sigma dash h is calculated k naught times gamma saturated minus gamma w, because here gamma saturated minus gamma w is nothing but a submerged density, that is gamma dash, below the water tables, that is the reasons. This equation indicates that the effective lateral earth pressure increases linearly with depth. At the top surface, sigma dash h is 0 because z is 0. At the bottom of the retaining wall, sigma dash h is calculated k naught times gamma saturated minus gamma w into h, because z is equal to h. The pore water pressure U varies linearly from U equal to 0 at z equal to 0 to U equal to gamma w into h at z equal to h depth. The at rest lateral force P naught exerted on the wall is the sum of the area of the effective lateral pressure triangle and the area of the pore water pressure triangle, that is P naught equal to, that is area of the triangle of first triangle plus area of the triangle, that is second lateral pressures. The point of application of P naught is located at a distance of, where it's at, h by 3 from the bottom of the retaining wall, because of the triangular distribution of the both the effective lateral earth pressure and the pore water pressures. That is the second case diagrams explanations. Figure 7.5e, this is this 7.5e based on these diagrams I already explained. Okay, figure 7.5e shows a retaining wall supporting a fill with a water table that is at a distance h1 below the top surface of the fill. In this case, we can assume that the soil below the water table is fully saturated. The distribution of the effective lateral earth pressure and of the pore water pressure are shown in figure 7.5f, that is 4f. Okay, so this distribution of pore earth pressure, see this, how these diagrams are this. Okay, next, at z equal to 0, at z equal to h1, at z equal to 0, sigma dash h equal to 0 and u equal to 0. At z equal to h1, then sigma dash h equal to k naught into gamma into h1 and u equal to 0. At z equal to h1 plus h2 is equal to h, so then sigma dash h equal to, that is bottom pressure, k naught gamma h1 plus k naught times gamma saturated minus gamma w into h1 and u equal to gamma w into h2, means height into density of waters. To calculate the lateral force, we can simplify the pressure distribution using triangular and rectangular shapes as shown in figure 7.5f. The area of each shape can be calculated separately to give us the lateral force that must be applied at the centroid of the respective shape. The sum of these lateral forces is the total lateral force exerted on the wall. The point of application of the total lateral force can be calculated by taking the sum of the moments of all the forces about the hill of the retaining wall and equating that to the moment of the total lateral force resultants about the hill. This will be illustrated in example 7.1 next class. Okay, no problems. A uniform pressure, that is surcharge, is sometimes applied at the top surface of the backfill. For example, it is customary to apply a uniform pressure of 15 to 20 kPa to simulate the effect of traffic loads on a retaining wall. A uniform pressure Q applied at the top surface causes an increase in the at rest lateral pressure equal to K0 times Q. Figure 7.6 shows how to account for the surcharge effect for a retaining wall with a dry backfill, a submerged backfill and a partially submerged backfill. This is explained in next class. Okay, no problems. So these are the references or reference for to cover session 5 of lateral earth pressures. Okay, thank you one and all. Next class I will be continue for next sessions.